Hi guys, so we've learned about ionic bonds and now it's time to move on to covalent. You have a note sheet that separates the two types of bonds from each other on the second page. So under covalent bonds you'll see that here are the things that make a bond covalent. First of all, it happens between two nonmetals. Remember that ionic is between a metal and a nonmetal, so if you have no metals, this must be a covalent bond that you're doing. In covalent bonds, atoms share electrons instead of transferring them. Remember, in an ionic bond, electrons actually leave one atom and go to another. But they don't do that in covalent bonds. They share electrons, and that's actually what co means. It means to share. Like if you're cooperating, you're sharing the operation. If you cohabitate, you live together, you share a dwelling. Covalent means that you're sharing a valence shell. And so the electrons in the valence shell are shared between two or more atoms. Because of the sharing that happens, you get something that's called polar molecules sometimes. And the word polar just refers to the idea that you have two sides to you. Like the planet is polar, it has a north and a south pole. But atoms are polar if they have a positive side and a negative side to them. So one side is positive, the other is negative. So I'll show you how this works with water. Water is a covalent bond because hydrogen and oxygen are both nonmetals. So I'm going to show you what it looks like to form a covalent bond. I have oxygen drawn here as a Bohr model, and you can see that oxygen has 8 protons and 8 neutrons, and he attracts 8 electrons. There's 6 in the valence shell. These 6 valence electrons are a little unstable, so to help stabilize oxygen, we're going to move in some hydrogen atoms to share electrons with the oxygen. Each hydrogen atom has 1 valence electron, and they can't give away those electrons because, I'll show you why in a second, but if I were to draw an atom of hydrogen down here, hydrogen has 1 proton, no neutrons. Here's the nucleus. And then around that, we've got 1 electron that I'm going to share with the oxygen atom. We can't give that electron away. We can't just have hydrogen give that electron to oxygen, because if he did, there would be no shell underneath to be full. And that's the only reason atoms would do that, right? For example, a lithium atom or a sodium atom can give away 1 valence electron because underneath they have a complete shell and that's stable. But hydrogen can't do this. Hydrogen gives away that electron and becomes more unstable. In fact, hydrogen ions, which is what you get when you strip away the electron that's going around a hydrogen atom, hydrogen ions are so unstable that they are what make acids so dangerous. If you pour an acid on something, it will try to suck all the electrons out of whatever it landed on and chemically react with whatever it can find to stabilize that very unstable hydrogen ion. So they don't do this naturally. Instead, hydrogen's going to pull in there and share that 1 electron with the unpaired electron in the oxygen atom. And we need 2 of them to complete this, so another hydrogen is going to come along and do the same thing over here. Like so. That's called covalent because they're sharing the valence shell. The oxygen now has 8 electrons in its valence shell, and each hydrogen now has 2 in its valence shell. And remember, hydrogen is full with 2, so that's everybody's happy in this circumstance. But this sets up a situation where because they're sharing them, they wind up not necessarily sharing them equally. And you might wonder why that is, and it's because protons are positively charged, and they are what attracts electrons in the first place. So if you think about it, this oxygen atom with his 8 protons is a big draw for electrons. That pulls electrons towards it. And the 2 small nucleuses, or nuclei as we would say, for the 2 hydrogen atoms have only 1 proton each. So even though they can attract electrons to them, they can only attract them with a lot less strength than the oxygen can. So as a result, the negatively charged electrons tend to spend more time on this side of the molecule. And because they're pulled away, the electrons of the hydrogen atoms are pulled away to the upper right here, the bottom left of this molecule picks up a positive charge. So this is what we mean by polar. Water molecules have a positive side and a negative side to them. Where the hydrogen Mickey Mouse ears are has a slight positive charge, and where the oxygen side is, the head, is where the negative charge is. And this is why water does all those interesting things. For example, water is very clingy. It clings to itself. It beads up on a surface, right? All this rain we've been having, you look outside at your car windows and you see little beads of water all over it. Other liquids don't do that as much. For example, we compared water's clinginess to alcohol's clinginess when we put little drops on our whiteboard, and you should have noticed that water beads up like this and alcohol spreads out kind of almost flat. And that's because alcohol particles don't have these positive and negative charges. They are covalently bonded, but they don't have a polar side to them. So as a result, alcohol particles are not as strongly attracted to one another as water particles are. This is also why water is more dense. The particles are just drawn closer together. It's also why it's harder to boil water away than alcohol. Water boils at 100 degrees Celsius, alcohol at about 80 degrees Celsius. And that's because it just takes more energy to pull apart water molecules because of these charges. It's also why water does that weird thing where when it freezes, it expands, which is backwards to the kinetic theory. According to the kinetic theory, things should expand when they get hot. And water does that, but when it freezes, it expands much, much more because these positive and negative charges, when water freezes, they have to freeze away from each other, so that a positive charge is attached to the negative side of the atom that it's next to. And as a result, they form a strange crystal that has a hole in the middle, and it takes up a lot of room for them to do that. So covalent bonds can be polar, but they don't have to be. Let me show you a couple of nonpolar covalent bonds. Let's do chlorine gas. Chlorine is what we call a diatomic gas, meaning it is two chlorine atoms that are bonded to itself. Di means two, so diatomic means two atom. So this is a two atom molecule. So two chlorine atoms will bond to each other, and here's what they do. They each have 7 valence electrons, and instead of doing a Bohr model, I'm just going to do the dot diagram for chlorine. So it has 7 valence electrons. So if I were to put another chlorine right next door, like this, it may not immediately occur to you how to fit these two things together so that they can share electrons. But they're going to share here and here because those are the two empty spaces. So what I have to do is spin the two chlorines around, or spin one of them around so that the open spots line up like a jigsaw puzzle. And when you do that, you're going to see that the two will fit together like this. You'll get the two chlorines have to line up like so that the two open spots are next to each other. This one slides this way, this one slides that way, and the final result looks like this. That's how you draw a covalent bond. For water, which we did before, it would look like this. You have the oxygen, and you just pop in the hydrogens in those empty spots, like that. So this is how you draw covalent bonds. Usually it's a good idea to start by drawing the largest of the atoms, if there's one atom that's bigger than another, and then seeing where the smaller ones fit in. There are lots of covalent bonds that have what are called double and triple bonds in them, but I don't teach that to you, so I will only give you covalent bonds to draw that are simple single bond ones where you have to just fit your electrons together so that everybody has a full shell. One last thing about covalent bonds. I want you to know these diatomic gases. These are all the gases on the periodic table that are made up of the same atom bonded to itself covalently. And there's a little acronym for this. It says Brinkelhoff, which is a German name, and it's a good way to remember all the different atoms. So bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine all form double bonds with themselves, and they all have except for hydrogen, they all have 8 valence electrons when they're done. So the hydrogens share like this. This is how you draw the hydrogen bond. You can draw them head to head also, like this, if you prefer. But all the other ones do like I was showing you with chlorine, where they just hang out right next to each other, sharing their 2 unpaired electrons share in the middle there. So covalent bonds happen between nonmetals. It's a sharing of electrons, and they can form polar molecules. Obviously, the diatomic gases are nonpolar because they share those electrons equally. Both atoms are the same. They both have the same number of protons, so both atoms pull on the electrons equally. On the other hand, something like hydrogen bromide does not share equally. So when hydrogen and bromine pair up, forming a covalent bond, The bromine will steal most of the electrons towards it, so this will be a polar molecule. There's one more example that I want to give you. Here's another covalent compound. This is the gas methane, CH4. And CH4 looks like this. All the atoms in group 14 have 4 valence electrons, and I taught you to draw them like this, just because I wanted to keep the pattern consistent. But all the ones in group 14 actually do something called hybridizing, where they will deliberately spread themselves out like this so that the top 2 actually separate to fill in that empty space. This is what makes carbon such a great atom for bonding, and it's the reason why living things are mostly made of carbon. And in fact, you may have heard the term carbon-based life forms. Carbon is like a Lego that has lots of places to attach to other things. So this carbon atom can share electrons with 4 hydrogens, and when he does that, I'm going to put the hydrogens in red. You can see that you get this nice symmetrical molecule. Each bond between the carbon and the hydrogen is polar because the carbon has much more pull on those electrons than the hydrogen does because the carbon's a bigger atom with more protons. However, the pull that's going on here is symmetrical. All these bonds are pulling in opposite directions of each other. So the molecule is considered nonpolar even though the bonds within it are polar. So symmetry can cancel out polarity. So you have to look for 2 things to determine whether something's polar or not. Determine whether or not if they're 2 of the same atom, definitely nonpolar. Then if the atoms are arranged in a way that makes the bonds symmetrical, also nonpolar. But if you have 2 different atoms and there's not symmetry, then you have a polar molecule. And that's something that you do need to know for your test. Okay, so that's it for covalent bonds, and I'll see you in class.